In a previous video, we talked about the benefits that Meta receives when the company releases language model open source. It is a principle adopted from the very early days of research in AI. Even though Meta was criticized by some, they were pushing for a more closed environment. Today the positions have changed, as many other companies are releasing their models open source, like Mistral, Google Gemini, Microsoft Phi-2. The ultimate goal is to achieve human intelligence. In this video we look at how Meta is working towards this goal and how the company sees the future of AI. But first, let's hear the objective from Joelle Pineau, the Vice President's AI Research at Meta.
First and foremost, let me go back to our goal. Our goal is pretty clear. We do aim to reach for AGI and have this ability for AI to have human-like cognitive abilities across a wide range of tasks. And so that means that we need to have intelligence that can understand, that can learn, that can reason, apply knowledge, and perform tasks in a wide variety of domains at a level comparable or exceeding that of a human being. To do that with agility, adapting to new environments, new tasks, and to new situations.
Today there are thousands of models being developed that are small and big in size. But the general view is that AGI will be achieved by developing larger models. Here is how Meta AI sees it.
As we move towards AGI, we're increasingly moving towards models that are larger, with more general capabilities. And we may not see quite as many models being built, maybe not hundreds of them. We may see fewer, bigger models. But I suspect many of the smaller, more specialized models are going to continue to exist, whether for specialization or for efficiency reasons in many cases. And so the real power of our work is actually to be thoughtful about how we build out that strategy to accommodate the wide set of use cases.
One of the issues in developing larger models is that of controllability. That is, how to shape and control the behavior of an intelligence system. We don't want, for example, to give a robot the capability to attack its user.
Really, we are on a path to build more and more general model. That's the generality access. The one we talk about less, and is equally important, is the controllability access. This is the work that we need to do to shape the behavior of the model. Whether it's through training, whether it's to fine-tuning, whether it's prompting interaction, we need to be very thoughtful about the strategy that we deploy for controllability of these models. Having models that have generality without controllability, it's a little bit like having intelligence without socialization. It's intelligence that doesn't have purpose, it doesn't have values, it doesn't have guardrails. And so our goal over the next decade is to build all the components we need for general intelligence, but also have the ability to shape that intelligence, interact with it in a way that's meaningful.
A large model that addressed generality and controllability was described by Meta chief AI scientist Yann LeCun in a paper titled A Path Towards Autonomous Machine Intelligence. This paper is still the blueprint for Meta AI. Here is how Pineau summarizes it.
The paper calls out many different areas of work that we need to make progress on. First and foremost, a perception system where the AI agent needs to learn through observation interaction, a memory module in terms of tracking both short-term information as well as capacity to store and reason about long-term information, an actor module that can actually execute plans, whether this is for digital agents, virtual agents, physical agents such as robots. We need to be thoughtful about building cost models. I talked about the controllability and shaping of the behavior. A lot of that information resides in the cost model that enables us to align the behavior of the agent towards our goals and preferences. And at the core of all this is a world model, a digital twin of the real world built from data, which we can use for reasoning and planning. A good world model has the ability to make accurate predictions about future events, including when we condition on very rich multimodal information or on actions. And this is essentially a universal prediction model. And so in many ways, this is the real goal for the next few years, to move from word models to world models.
At this time, Meta does not have a blueprint for creating a world model, but researchers and engineers are working on some hypotheses. 3 in particular are under consideration. but there is room for more areas of exploration. These hypotheses are creating larger models, using different type of data like video, and use the brain as a model. Here is how Pineau illustrates this hypothesis.
One hypothesis is that scale is everything. This is a popular view. We just keep on building bigger and bigger word models, and somehow we will capture a representation that consists a world model. This has definitely yielded amazing progress in recent years, but it's not clear that there's a path right now for these models to actually understand phenomenons related to causality or compositional representation, which we know are hugely important and very common in human intelligence.
The second hypothesis has to do with the constructions of a world model, something that we presented also in a previous video.
A lot of the foundation models today are actually trained purely from observational data. Data that's collected offline in relatively static conditions without an ability to really interact with the world. Yet we know from humans and animals that the interaction component is so important. The ability to explore, manipulate, interact, run experiments is absolutely crucial to understand the basic principles of causality, to understand the laws of physics and the properties of objects. And so an important hypothesis is that we will reach AGI by building world models that can be used to run forward simulations with sufficient accuracy that we can actually use them to reason and plan without suffering the compounding error, and use that across multiple levels of spatial and temporal resolution and abstraction.
A third hypothesis to create a world model has to do with the human brain.
There's a third hypothesis, in case the first two don't work out. Third hypothesis is to focus a lot of efforts on understanding the human brain and possibly create a full simulation of its capabilities as a prerequisite to achieve machine intelligence. Now, to be honest, there's actually a lot of skeptics about this one, and it's not necessarily the one we are pursuing most aggressively. Nonetheless, looking at the human brain may have some important clues in terms of inductive biases to really close the gap in terms of some of the challenges that we face, in particular when it comes to learning efficiency, when it comes to value alignment, and it comes to consensus building through social interactions. There may be interesting clues there.
Some voices in the industry are wondering if neural networks themselves need a new structure or a different approach in order to behave like the brain, which can generalize with very little data. For Pineau, this is just another hypothesis that should be explored.
There are a number of hypotheses of what we need to change in terms of how to do it. I think some people just think we should just keep on pumping more data into the model, and out of the sheer quantity of data, some of these properties will arise. I tend to be a little bit skeptical of that. I do think there's something we can do, and in particular, this notion of spatial and temporal resolution, the hierarchical resolution, I don't know that it will come out directly out of the raw data. So I think we have space to look for mechanisms in terms of different types of activations, in terms of different architectures, in terms of different loss functions. And we have a group of people who are exploring many of these hypotheses. What helps is to be very rigorous about the experimental process for doing that. So what you want to do is cover a wide range of hypotheses quickly and know quickly whether there's some promise there or not.
And this is exactly the approach that Meta is taking, not options left behind.
Finally, some of you may have sympathies for hypothesis number 4, which really focuses on building our understanding from first principles, building that in terms of the basic theory. At this stage, honestly, we need to make progress across all of these. And over time, we're going to learn from all of them how to solve this.
The hypotheses and views expressed by Pineau should be taken into great consideration. Only a few months before her presentation at NVIDIA GTC 2024, she was a guest at the French event Vivatech. She expressed some personal opinions on stage about what to expect for the future, and today we can say that she was quite right. Take a listen.
I will pick out 2 aspects that I think we should expect to see in next generations of models. One of them is I do expect significant progress with respect to so-called hallucinations. And so in particular, having much better verification and factuality of the models. I expect we'll see a step change. We have talked so much about this problem, I do not see a path that someone will release a model where we haven't seen a significant improvement on that. The other place I expect to see quite a bit of change is in terms of the ability to deal with multimodal information. So bringing in, and already GPT-4 does some of this, but really understanding information coming in from a much wider set of modalities. And the reason we will need to move in that direction is because more modalities means more data. And to get a better model, you need more data. And so more modalities in, but probably more modalities out also in terms of the ability to generate is something I'd expect to see in the coming generations.
In order for all the hypotheses to be tested and predictions to come true, there is one component that is absolutely necessary and very few companies can afford: a huge and state-of-the-art infrastructure that can be flexible to accommodate current and future research. This infrastructure at Meta is getting even bigger. Take a listen.
Looking in the future, Mark has already shared the scale of our ambition, the investments that we're making. This includes 350,000 H100s by end of year and overall 600,000 equivalents, H100s equivalents over time. Just last week, we also announced publicly our latest implementation of 2 training clusters, in this case on the order of 24,000 GPUs. We'll see whether the announcements of this week change the longer-term plan, but certainly for the next year or two, I think we're incredibly well set up to be doing the research that I've shared with you today in terms of our roadmap. We are also working on a family of recommendation-specific accelerators, ASICs, internally for our more specialized inference workloads, for that to work at scale, for that to be as efficient as possible. We see this as being highly complementary to the GPUs that we are investing in for the training workloads. We are also redesigning a lot of our data centers to bring new capabilities online, and we expect those to really dwarf our previous research superclusters. Part of the challenge is investing ahead of the curve when this capacity is needed, and so these investments represent huge long-term bets in terms of the future of AI, the future of technology. Today we have 23 different locations with a number of these still under construction. It's also a place where we have actually a strong track record of driving progress through an open approach, for example, through our Open Compute project in which we've been participating. And finally, really foundation to our approach is a strong partnership with the hardware community